So our next dynamics problem is actually a kinematics problem, and we're going to study this system right here. And rather than show you a static picture, I think it's probably best to show you a computer-generated animation. So there it is. We've got this rod that's in green. It's rotating about a fixed point. Right there, it's rotating, looks like counterclockwise, and then at the end of the rod there's pinned to it a disc that rotates the opposite direction. And what I want you to think of when you look at this is maybe an amusement park ride. We're looking down on it from above, kind of like the teacups. I'm not sure what kind of amusement park ride it is, but you can imagine a rider standing here at this yellow dot, and it's going around a rather complicated path that's determined by these two rotations. And what I'd like to do now is study the kinematics of this system. So let's define a few things. We'll call the radius of this disk, call that r, and we'll let the length of the rod be L. And we'll assume that the length of the rod is twice the radius of the disk, so L equals 2r. As we saw previously, we say that the arm rotates counterclockwise at a rate we call omega. And here the omega would be measured in terms of radians per second or something like that. And as we saw in the animation, the disk itself rotates the opposite direction, that is clockwise, at a rate 4 times omega relative to the arm. The way you think about this is there might be some motor embedded in the arm and in the disk, so it spins the disk relative to the arm at a rate 4 times omega, where omega is the original rotation rate of the arm. So the first question I ask is, what is the angular velocity of the arm? So I want you to think about this. Pause the video, answer it, and when you're ready to check your answer, start the video up again. Okay, so the first thing to note is that angular velocity is a vector. In other words, it has a direction. Remember, angular velocity is a rotation rate, and the way the angular velocity vector points is along the axis of rotation. So here we have the arm. The arm is rotating counterclockwise in this plane, so the axis of rotation is perpendicular to the plane. In other words, the axis of rotation is perpendicular to your screen here. And the direction is either into the screen or out of the screen. Which way is it? Well, to do that, you pull out the right-hand rule. Right? You take your right hand and wrap your 4 fingers in the direction of rotation. So if you take your right hand and wrap your 4 fingers in this counterclockwise direction, your thumb will be pointing out of the screen. So the angular velocity vector is out of the screen. So the way I'm going to define vectors here, I'll call E hat 1 the direction radially outward. I'll call E hat 2 the direction perpendicular to that. So if I take the vector cross product, E hat 1 cross E hat 2, then I get a vector pointed out of the screen. I'm going to call that vector K hat, and therefore my angular velocity vector is going to be in the K hat direction. Now I get the angular velocity vector, omega arm, let's say. The angular velocity of the arm would be in the K hat direction, and it has magnitude omega. Omega is the rotation rate, so omega rotation rate in the K hat direction. There's my angular velocity of the arm. So the next question I have for you is, what is the angular velocity of the disk? Yeah, think about it for 1 second. Actually, if you just think about it for a second, you might say omega disk is just 4 omega in the K hat direction, or 4 omega in the minus K hat direction, since it's going the opposite direction. But that would be wrong. I want you to think about it a little more carefully than that. All right, pause it now and then come back when you're ready to check your answer. All right, so to answer this question, I'm going to draw a little picture here. So let me make some room. There's my picture. It's supposed to be the arm and the disk. And let's say in some amount of time, I'll call it a little delta t or something like that, the rod rotates counterclockwise an angle theta. Well, in that exact same amount of time, the disk should rotate an amount 4 theta, right? It's rotating at 4 times the rate. But it's rotating at a rate 4 times the rate relative to the disk itself. So if I take a line that's fixed to the disk, it's going to move that angle 4 theta. But let's think now. To define an angular velocity, we need to find the angle relative to some fixed reference. Over here, I use the fixed reference as some horizontal line right here. So I should do the same thing when measuring the angle displacement of the disk. When the disk moved at an angle 4 theta relative to the rod, it moved an angle 3 theta relative to the horizontal here, because the rod itself moved an angle theta. right? So this theta is the same as that theta, right? So again, the rotation of the disk relative to some fixed reference is just 3 theta in the clockwise direction. Therefore, the angular velocity of the disk is given by the following, right? If the angular velocity of the arm is omega in the k-hat direction, then the magnitude of the angular velocity of the disk is 3 times omega, right? For every theta the disk goes up, for every theta that the rod or the arm goes up, the disk has to go down 3 theta. So you get 3 times the angular velocity, and it's in the opposite direction. So this angular velocity is in the minus k-hat direction. So there's my angular velocity of the disk. And of course, there's another way to write this. In other words, I can say the angular velocity of the disk is equal to the angular velocity of the arm plus the angular velocity of the disk relative to the arm, right? We saw that the angular velocity of the arm was an omega in the k-hat direction. The angular velocity of the disk relative to the arm was a 4 omega in the minus k-hat direction. And you add these two things together, what do you get? You get minus 3 omega in the k-hat direction. That's exactly what we had before, right? So we see that the angular velocity vector behaves like other vectors that we've seen, right? With these relative relationships. Nice. In fact, you can see this concept of relative angular velocity in the animation too. So what I want to do is take this animation of our system and look at it in a frame of reference that is rotating with the rod. So here's it in the regular fixed frame, but what I want to do is I want to put myself in the frame of the rod itself, this green rod, this arm, and rotate with that arm. So here I am in this frame of reference that's fixed to the arm. It looks as though the arm is stationary and the rest of the world is moving around you, right? So what I want to do is look at this reference line right here. And I want to look at how many revolutions that the disk makes as the rest of the world goes through one complete revolution. You get that? So as this thing goes around one complete revolution, I want to count how many times the disk goes around. So here we go. So here's the beginning. And I went around once, here's twice, here's 3 times, and here's 4 times. It was 4 times because remember the disk is rotating at a rate that's 4 times faster than the rate of the rod itself. So when the rod goes through one complete revolution, the disk, at least from the viewpoint of the rod, it goes around 4 times, right? So you see that 4-to-1 relationship right there. Okay, now I'm in the fixed frame again, looking at this, the rod rotating. Now I'm going to look at this. We'll start right there. There's where we started. There's 1 revolution. Here's the second one. And now the third one. So now it's a 3-to-1 relationship, right? So in the fixed frame, it's a 3 revolutions for the disk for 1 revolution of the arm. Whereas in the rotating frame with the arm, it's 4-to-1, right? That demonstrates the relationship between the relative rotation rate to the actual rotation rate that we discussed mathematically. Now the next question I have for you is, what is the velocity of point P? Now point P is this point right at the center of the disk, right? What's the velocity? I'm not asking for angular velocity, but the actual velocity of that point. Now this point P doesn't just belong to the disk, it also belongs to the rod. And since it belongs to the rod, it has to always remain a constant distance from this central pivot point of the rod, right? So the distance between this point O and the distance P has to be a constant, and so therefore as P is moving around, it has to move around in a perfect circle centered about point O right here in the middle. So let's think about this. The velocity of point P therefore has to be tangent to that circle, right? It has to be tangent to the circle. And if I show the velocity vector in the animation, there it is. You can see it right there. That light blue vector, there's my velocity. And there it is, tangent to the circle. So therefore, I expect this velocity of point P to be in this E hat 2 direction that we defined before, right? And since it's going around a perfect circle, I might use my previous knowledge of polar coordinates. It'd be an r theta dot in the e hat 2, right? That's what we've known from before, but when we're dealing with kinematics of rigid bodies, we like to write this a little bit differently. In other words, we write it in terms of this vector cross product where we got omega cross r. Omega here is the angular velocity of the arm. Remember, that's in the counterclockwise direction, or the actually angular velocity vector is in the positive k hat direction out of the screen. Vector cross product with a p relative to the point we're rotating about. Position of p relative to O is this vector right there, drawn right there. So again, velocity point p is this vector cross product. So the angular velocity of the arm, remember, was omega in the k hat direction, and the position of p relative to O is the distance L in the e hat 1 direction. E hat 1 is already defined up there. So all I have to do is take this vector cross product, and I get omega times L. You know, these two vectors are perpendicular to each other, right? K hat is straight out of the screen. E hat 1 is pointing radially outward. Take the vector cross product of these two things, I get a vector in the e hat 2 direction. Voila, and that's what I get. So I got omega times L, which is the same thing as r times theta dot. Got these two symbols in the opposite order in these two cases, but that's the exact same thing I had in the polar coordinates. And if I take my previous statement that L is twice the radius of the disk, then I get the VP equals 2 omega r in the e hat 2. And that's my answer right there. And you can check your units too. Omega had units of radians per second. It's a 1 over time. R has a distance length, so this is a length divided by time. And that's what a velocity should be. So we're good. And there's my velocity. And it's precisely this velocity we see right here. Again, it's a constant speed. It's always tangent to the circle that the center is traveling on. Now the next thing I want to do is perhaps a little more interesting. Definitely a little more interesting. See this yellow dot here that's on the disc? That's the person riding on the carnival ride, right? And what I want to do is consider the velocity of that person, the velocity of that little yellow dot as it's moving around. You notice that sometimes the yellow dot is outside the circle, sometimes it's inside the circle. I'm talking about the circle that's traced out by the center point. So you can see that this path taken by this yellow dot is quite a bit more complex, let's say. In fact, if I trace out the path that little yellow dot makes, look at this thing. Isn't that beautiful? It's cool little flower-shaped figure. I don't know. I can watch this thing all day. That's awesome. That's beautiful. In fact, check it out. Look at this. I've added a vector here representing the velocity of that yellow point. And you can see it is always tangent to the path. Isn't that cool? I told you at the beginning of the semester, right? Velocity is always tangent to the path. And there's the actual velocity vector. Now what I'd like to do is actually calculate this velocity vector and see what it is, see how big it is, and which direction it's pointed at various points along its trajectory. So that's what we're going to do next. So what I want to know are the velocities of points on the edge of the disk. So I've already seen that point right there, but this point can be anywhere on the edge of the disk. So maybe it's over here, or over here, or over here. I'm going to label these 4 points right here. I'll call this one point A, B, C, and D, as so. And here what we do is we use our notion of relative velocity. So in particular, we can say the velocity of point A here is equal to the velocity of point P plus the velocity of A relative to P. And we can say the same thing about the other 3 points as well, D, C, B, C, and D, right? Velocity of B is equal to velocity of P plus velocity of B relative to P. And same with C and same with D. In each of these cases, velocity point P is the same, right? It's the velocity of this point P, which is the center, right? The center is just going around in a perfect circle around this fixed point O, as we've seen already. So in each of these cases, VP is the same. What makes the velocity of these points on the outer edge of the disk different is that are these relative velocities. Remember what these relative velocities mean. That means for velocity of A relative to P, for example, means we're sitting on P looking at A and looking how it's moving. Similarly, for velocity of B relative to P, we're sitting on P looking at B, and it has a different motion than A does. So what does that look like? So here's another viewpoint of that disk rotating around, but now I've changed my plot axis, so I'm following this point P, right? This is the center of the disk. I want to know the velocity of these various points around the edge relative to the center. So here I'm at the center looking at everything else. And when I'm looking at everything else, it's just going around in a perfect circle around the center, right? Don't be distracted by the rod over here, by the grid points. That just indicates that everything's moving. But I'm focusing, I'm planting myself at point P here. I'm looking at everything else, and I'm just seeing just this almost the simplest possible motion you can imagine relative to point P here. It's just going around in a simple circle relative to point P here. All right, so let me go back to my mathematical expression. So for all these relative velocities right here, let me lasso them, get rid of them. I can replace those with a vector cross product. So in place of the velocity of point A relative to P, I can write omega d. This is the angular velocity of the disk, right? Vector cross product with the position of point A relative to point P, right? The same expression we had before. And I can do the same thing with the rest of these. And these are the rest. So remember this d, the subscript d on these angular velocities, the omega, that's the angular velocity of the disk, right? Not the angular velocity of the rod, but the disk. And here are our expressions. And these velocities are just the ones that I've shown right here, right? These are the relative velocities, the velocity of point A relative to point P. Well, A is just going around in a perfect circle around point P, so it's tangent to that circular disk right there. Similarly for B and C and D, they're all sort of just rotating around from a relative perspective, right? Relative to point P, they're just rotating around the disk. All these relative velocity vectors have the same magnitude as 3 times omega times r, and they're in either e hat 1 direction or minus e hat 1 direction or e hat 2 direction. This is supposed to be a 2, or minus e hat 2 direction. So all of them are just marching around in circles. And that's all there is to it for these pieces. So the velocity of point A, for example, is going to be a combination of this velocity of point P plus this velocity of point A relative to point P. So it's a vector sum of those two vectors. Likewise, at point B, it's a vector sum of those two vectors. In fact, let's look at it in the animation again. Now the result of this vector addition is seen in this animation right here. So the solid light blue arrow, that's the actual velocity, and you see that it's always tangent to the path. It's tangent to this yellow curve that's being traced out through space. So that velocity vector is the vector sum of these other two vectors you can see on here. They're the ones that are not solid. They're the ones that are sort of outlines of vector. In fact, let me pause. How about, can I pause? So let's pause right here. So for example, my vector is this one right there. There's my velocity vector, but it's the sum of these other two vectors. So notice this vector right here, this vector is VP, right? There's velocity point P. It's right there. It's tangent to that red circle, right? And I've transposed VP and I put it up here. So there's VP. And then here's the velocity of this point on the edge of the disk relative to point P. Notice that this one is tangent to the disk itself, right? The disk is rotating clockwise. You can see that this is an arrow pointing in that direction tangent to the disk, as if it were moving around clockwise about point P. So that resultant vector right here is the vector sum of these two different vectors. And I can let this thing go for a little bit, and maybe I'll stop it over here. Now you can see a vector sum that way. Again, here's VP. It exactly matches that VP. And then here's the relative velocity, again tangent to the disk. And you can see how it just sort of, these two vectors sort of beautifully add together to get to the full velocity. Do you see how those things work? Wow, that is just so cool how they add together. I can just stop it anywhere. There's VP, it's tangent to that VP. Here's that relative velocity, it's tangent to the disk. And we just see this thing just sort of develop quite naturally. Yeah, just look at that for a while. It's just beautiful the way these things add together. And that gives you the trace of the curve. In fact, the vector that traces out that curve. So now I want to look at this at specific points. How about at point B up here, where you're aligned, you're farthest away from the pivot point O, and how about point D down there? How do these add together? So come back over here. And I'll stop it exactly right here. So here we're at point B. So this was point B that we said over here, right? There's point B. Here's point B. So you'll notice that velocity at point B is the vector sum. So here's VP, right? It's the same as the velocity at point P. And then the velocity of point B relative to P is actually in the exact opposite direction. That's what we said over here, right? The relative velocity is in that opposite direction of VP. Therefore, these two vectors that add up to our velocity, they partially cancel each other out, right? So the result is this tiny little vector right there for our velocity. So when we're at point B out here, the speed is very small, or at least the smallest it ever gets, because these two velocity vectors are partially canceling each other out, right? So at point B, those velocities are, again, very small. Now when we look at them over here, this would be the equivalent of point D down here. Here's where the VP and the relative velocity are adding to each other, right? They're both pointing in the same direction. In fact, let's go back to my animation. So here we see that these two vectors, there's the VP, it's the same as that one. And here's the relative velocity out there, is that one. These two are adding together to get a big velocity, which adds up together over there. So when we're close to the pivot point in here, we're going at our fastest when these two component vectors perfectly add to each other, right? So you can see as this thing goes along, they're adding or subtracting, they're going in different directions, but they add up in beautiful ways. So again, when I'm at point D, I'm going my fastest. When I'm at point B, I'm going my slowest. And you can certainly see it in the picture. Point B, where I'm going the slowest, that's these little lobes right here. I slow down when I'm at these little lobes. You see it slow down right there. And then it speeds up when it gets down to these low troughs down here. So you can see it speeding up, going really fast, and then slowly with the lobe, then speeding up to go really fast, then slowly in the lobe, then speeding up and going really fast, and slowly in the lobe. Notice in these lobes, it turns around and actually heads backwards a little bit. Right? VP is always along that circle here. It's always going in one direction. But because of this interplay between the two vectors, sometimes right here the point on the edge of the disk is actually heading in the exact opposite direction, right? They reinforce each other down here, and then they fight each other when we go back here, and the relative velocity wins out, which pulls it backwards, which is kind of cool. I love how this thing works. Now I know this video is getting long, but before we wrap up, I want to ask one more question. First of all, you'll notice that on the edge of the disk, the velocity never goes to zero. It gets very small at the very lobe of this, or at the very end of this lobe, but it never actually goes to zero. So my question is there a point somewhere on this disk where the velocity goes to zero, at least for an instant? So here I've reframed that question. Is there a place on the disk where the velocity goes to zero, where the disk is just for an instant, motionless, zero velocity? And I'm not going to give you, well, I'm going to say yes, it is possible, but how would we find that? How would we find that? Well, remember, the velocity at any point on the disk can be represented by the sum of two different velocities, right? The velocity at point P plus the velocity of this whatever point relative to point P. So we need these two vectors to exactly cancel out to zero. And you'll see on this line between point D and B, here's where the vectors are collinear, at least, where they can possibly cancel each other out, right? If they're someplace out here, the relative velocity is going to be in a different direction than the velocity of P, so there's no way they can cancel each other out. So if it's going to happen, it has to happen on this line between D and B. In fact, we can narrow it down more, because notice that between D and P, the relative velocity and the velocity at point P, they sort of reinforce each other. They add to each other. So that's definitely not going to go to zero. But between P and B, here's where the velocity at point P and the relative velocity go in opposite directions, so they can cancel each other out. So as I get very close to point P, the relative velocity goes to 0, and I just have point P left. But way out here at point B, we notice that the relative velocity is dominated. So there must be some place somewhere in the middle here where they do exactly cancel each other out. And I'll let you figure out how to find that place. All right? I'll let you do that. But I'll show you what it looks like when you do find that place. All right, so here it is. So the lighter, the yellow curve, that's the one we had before. That's the one that makes this loop and turns around and goes backwards. And this sort of medium orange curve here, this is the one that's special. It does not have one of those lobes. It comes to a nice sharp point right there. You see that sharp point? That's where the velocity goes to 0 for just an instant. In fact, you can see it if I sort of stop it. Oops. Yeah, stop it at the right place. So let me bring it all the way back around again. And we'll look at it. But do you see those paths are different? And I'll try to stop it right there. So you can see there's VP right here. And there's VP. And here's the relative velocity for that point. And those two vectors exactly cancel each other out. So that's why they come to this sharp point right there. Sharp point. No little loop around, or no little shallow loop. But a sharp point where the velocity goes exactly 0. So you can see in this case, or in the case above over here, this is where it doesn't go to 0, and you can see a net velocity out of it. Over here we got a net velocity the other way. But at this one point right there, we got 0 net velocity just for an instant. Kind of interesting. That point right there has ramifications for other sort of kinematics types of problems. So I want you to keep that one in the back of your head. All right, so that finishes this particular video about the velocity kinematics of this disc and arm rotating mechanism thing. It's actually quite pretty, if I can say so myself. Just look at that thing. I'll let it run for a little while. Over and out.